Hey guys, my name is Kevin Reed and I'm going to teach you about Ampere's law. So the general form of Ampere's law is the integral over a little path, and the little circle means that it's a closed path, which is important, as we'll see later, of the magnetic field times each little bit of that path. And that equals mu 0 times I enclosed. This is just the enclosed current inside this path. So basically you draw any old path, little loop, and you have a current here, maybe another one here, and you add up, and if they're in opposite directions they cancel. So the sum of this is positive and this is negative, and the sum of those is that times that equals the integral of the magnetic field along this loop. But this magnetic field is not going to be constant, and that is going to get really ugly. So instead what we do, I'm going to grab an eraser, is we get rid of this Amperian loop. Usually we only have one current, which is a lot nicer, and we make something that has a constant magnetic field, like so. And if this was an actual circle and not that, then it would have a constant magnetic field around it, and we could, then this whole thing would just be the constant magnetic field times the distance of this loop, which is 2 pi r. And that then equals mu 0 I enclosed. And if we solve for B, we see that we have just come up with the equation for the magnetic field around a long straight wire. That equals mu 0 I enclosed over 2 pi r. Let's box that. And that is in your book. So you're probably wondering what an integral over a line is, and I was wondering this too when I first saw it. So basically it's an integral over a line. That's kind of obvious. But what that means is that, say we're in the x and y plane, like, real space, and we have a flat plane. This is x, this is y, and we have there's a scalar point at each field, say a magnetic field. So like here there's a magnetic field of 2, and here there's a magnetic field of 1. But instead of integrating along the x or along the y, we want to integrate along some random path we choose. And this is how you do it. This is a line integral. You follow this line, and you take the magnetic field at each point and you add it up. So instead of going, say, along the x, along the y, which is what a normal integral is, we use this. That is another question mark. And what's really important about this is that we get to choose our own path. So we don't have to choose something crazy like this. Say we have, again, a wire with current, I. We can choose a path that has a magnetic field that is constant. And this is very important because then we can actually find the magnetic field and find the, Ampere's law was up here, we can actually find the magnetic field as a function of the current, especially if it's constant, which is good. So we proved the magnetic field around a long straight wire, but now we're going to prove the magnetic field inside a long straight wire. So I'm going to draw the wire a little bigger this time, say like that, and it has a current I inside of it. And this is the center, and we want to find the magnetic field at a point that is a distance r away. And the entire wire has a radius of r, like that. And so we go back to Ampere's law, which is the integral around the loop. We're going to choose this loop because that has a constant magnetic field. So B times each little part equals mu 0 times the enclosed current. Now, the current enclosed is not just I, because the current is completely evenly dispersed around this entire wire, over this entire wire, so we have to find the fraction of area that is enclosed. So that's proportional to r squared over big R squared, because this area is pi r squared. Is pi times r squared. And the total area is bigger pi times r squared, and we can just cancel the pi's. And then we get this times I, and so this is the current enclosed, right here. And so we can plug in and solve, and we get B equals mu 0, and because there's this r and there's another r here that's going to be divided, we just end up with 1 r on top times r over 2 pi r squared. And that is the magnetic field inside a wire. And if you take note, this time it's proportional to the radius, whereas last time it was proportional to 1 over the radius. which means that it starts at 0 in the middle and gets up to a maximum right at the edge of the wire, and then it decreases to infinity. Good stuff. The last thing we're going to do is derive the magnetic field inside a solenoid. So this is a solenoid, basically when you have a battery running a current through a bunch of loops of wire, and we've already seen this. So we know this is the magnetic field inside a solenoid, but now we're going to prove it using Ampere's law. This is a cross section of a solenoid. It has a bunch of currents coming out of the board. As you can see here, the current's going to come and then come out of the board over the top and then go into the board around the bottom. So what we're going to see, using our right hand of course, is that the magnetic field is going to go that way. And so here, what we're going to do is draw a little loop, although it's going to be a rectangle this time. And it's going to go this way, then round, and then this way, and back around. So it has to be a loop because remember, it's the integral over a loop for Ampere's law. But we know that the magnetic field outside of a solenoid is 0. And then these lines, since they're perpendicular to the magnetic field, they actually don't add anything to the integral of b ds. So really what we're counting is this line. And the magnetic field is constant inside a solenoid. So the integral over a loop of b ds for this loop really just equals the magnetic field inside that solenoid times this distance, which I'm going to call d. And so BD equals mu0, and now we have to find I enclosed. So what we know is that there are going to be a certain number of wires passing through this area, and they're each going to have current I. So this is going to equal I enclosed. It's going to equal big N. This is just the number of loops times I, which is the current running through them. Over here, we're going to have I N. Now this looks really similar, except this is a lowercase n. And what the lowercase n represents is how many wires are passing through per unit length. And you see we have a unit length over here. So what we're going to end up doing is divide by that. mu0 I big N over D equals mu0 I little n. And we are done.
Do a dance.
Do a little dance. Make a little love.